Hello everyone, I'm Donghui from Institute of Computing Technology, Chinese Academy of Sciences. I'm very glad to introduce our work, a deep dive into DNS Query Failures. This is a joint work with my advisor, Professor Zhenyu, who is also from ICT-CAS, and Professor Gareth Tyson from Queen Mary University of London. We all know the importance of DNS in most internet-scale distributed systems. Nearly all internet-connected applications depend on DNS. Failures within DNS can have a dramatic impact on the wider internet, most notably preventing access to any services such as web and mobile apps that are dependent on domain names. For example, in 2016, a DNS operator Dyne suffered a major denial of service attack against its infrastructure. This meant that DNS queries for popular domains such as Netflix and Visa began to fail, crippling access to these services, even though those services were still online. So we're specifically interested in failures caused by DNS infrastructures instead of NX domains caused by, for example, typos. Besides, our high-level observation shows that DNS failures are commonplace, and this motivates us to inspect which factors correlate most closely with failed queries. To understand how and why DNS queries failed in the wild, we gather a unique dataset containing 3 billion DNS queries. Our dataset consists of passive DNS logs that are generated by deep packet inspection appliances in 3 ISPs in China. Each deep packet inspection appliance parses the DNS response messages from recursive resolvers to end users and generates a log for each response. A log includes the end user's anonymized IP address, BGP prefix, the autonomous system number, the recursive resolver's IP address, the DNS query type, all the resource records, the timestamp in seconds, and an indicator about whether the resolver and the end user's original IP address share a common /24 prefix, which is then used for identifying ISP resolvers. In cases of CNAME responses, we follow the redirection to the final record. The dataset contains 14 samples that were collected every other day in February 2018. Each sample consists of 10-minute logs generated by all the DPI appliances of the 3 ISPs. In total, we obtained about 3.1 billion logs. It's noteworthy that while there were IPv6 addresses in the response IP list of quad A queries, no IPv6 addresses were seen in end users' IP addresses and recursive DNS resolvers. We emphasize a few points about ethical issues. The ISPs collect the DNS logs for the purpose of improving their service quality and security. The end users' IP addresses were anonymized, and we are unable nor allowed to link queries to users. Users are notified when subscribing to the networks that the ISPs may collect this information and may share it with academics for research. Our study has not triggered the collection of any new data. As mentioned before, we are interested in failures caused by DNS infrastructures instead of NX domains. However, we do not have the response code in our dataset and thus are unable to check for no error, NX domain, or other status. To address this problem, we turn to a heuristic method to filter out logs that are attributed to NX domains. First, we check if the requested domain contains a valid answer. For example, for an A query, at least one resource record in the response is an A record of the queue name. We extract failed queries of the 4 most popular types of records that constitute 99.5% of all queries. Then we remove logs containing domains that have never succeeded in the whole dataset. Finally, 2.8 billion logs remain for subsequent analyses. Let's move on to the analyses. We begin by simply computing the number and types of failed queries in our dataset. This table shows the percentage of query types alongside the overall success rate. We present the 4 most popular query types. We observe a variety of success rates across the query types. The A-type queries account for the majority and are successfully resolved most frequently, while other query types manifest lower success rates. To our surprise, nearly 2/3 of the quad A queries failed. This confirms that a sizable fraction of queries is not successfully resolved, and we then explore factors influencing this trend. We first compute the distribution of failures across domains. Due to their prominence, we focus on A and quad A queries. This figure presents the CDFs of the success rates across domains encountered within our dataset. To eliminate the impact of low-frequency domains on the results, we filter out domains that issue fewer than 100 requests and use the remaining domains to plot the dashed dot lines. You can see that A queries exhibit high success rates. Nevertheless, as many as 7% of domains experience a success rate lower than 50%. Given that we have removed the failures caused by NX domains, the result suggests that problems with the DNS infrastructure do impact users when visiting these domains. For quality queries, about 60% of domains have never been successfully resolved. This suggests that there are infrastructural limitations in how DNS supports IPv6. The above results also suggest that the majority of failures are the responsibility of a small set of domains, especially for A queries. To explore this further, this figure presents the number of failures per domain on a log-log plot. We sort the x-axis by the rank of the domain based on the number of failures. We see that failures are concentrated on a small number of domains. To gain a further understanding of the types of domains that have high failure rates, we utilize the WebRoot Bright Cloud API to classify the top 50,000 domains measured by failure rate. This figure presents the results. The y-axis shows the top 11 categories sorted by failure rate, where the number of failed queries and the failure rate are shown in the parentheses. For each category, we plot the ratio of the number of failed queries of the top 3 TLDs to the total number of failures. An interesting observation is the concentration of failures for each category on the few domains. For 8 out of the 11 categories, over 80% of the failures are attributed to the top 3 second-level domains, top 1 SLD in most cases. Another observation is that a number of classifications which can be expected to fail frequently are present. For example, proxy, porn, and POC domains. This suggests that such domain types are paramount in increasing failure rates. In addition to domains that have high failure rates, another explanation for failed queries is that the resolvers may not correctly handle queries. To explore this, we identify DNS resolver by its IP address and calculate the success rate of queries issued to each DNS resolver. This figure presents the CDF of the success rate for the domains per resolver. In order to avoid bias, we eliminate the resolvers serving fewer than 100 queries in our dataset. The majority of resolvers have very high success rates when serving A queries. About half experience almost no failures. By contrast, 60% of resolvers serving quality queries can successfully resolve just less than 20% of their queries. Surprisingly, about 20% of the resolver never succeed in resolving quality queries. These resolvers may not be IPv6 ready during our observation period. Let's then move on to public resolvers. Closer inspection reveals that a notable set of queries are sent to public resolvers. Hence, we also inspect the reliability of these public infrastructures. We take into account some popular Chinese public resolvers as well as Google DNS and OpenDNS, which are widely used throughout the world. We identify these public DNS resolvers by the IP addresses offered on their official websites. We also identify ISP resolvers for comparison purposes. This table shows the number of A and quality queries handled by each public DNS resolver mentioned above, along with their success rates. We can see that Google DNS dominates the most used public DNS service, even though Google is less well known in China. Others do not show much difference in terms of query volume. We observe various success rates across public DNS resolvers, though. For example, DNSQuad, which belongs to Tyson, succeeds in almost all its A queries, while OpenDNS achieves just 86.3%. There's also notably lower success rate across all resolvers for quality queries. The above confirms that resolvers do seem to have an impact on success rates. So why do public DNS resolvers differ in success rates? We then explore two potential reasons. A potential reason for this is that the resolvers may simply receive different queries. To explore this, we compute a vector for each resolver, where each element represents a domain that appears in AL quality queries using the resolver and the query volume of that domain handled by the resolver. Then we calculate the similarity of each pair of DNS resolver using the cosine similarity between their vectors. This figure illustrates the result. We can see that the resolvers actually demonstrate a surprisingly low similarity with each other, signaling rather different request patterns. Among these resolvers, 114 DNS, which is provided by multiple Chinese telecom operators, and Ali DNS, which belongs to Alibaba, are the least like the others. Indeed, Ali DNS handles many requests of Taobao.com and Alipay.com, which belong to Alibaba's services, while 114 DNS handles many requests for Akamai domains, which appear less often in other resolvers. This could be the reason for the variance of success rates observed from different resolvers. Another possible explanation is the differences between resolvers' infrastructures. To explore this, we compare the success rates of the same domains handled by different resolvers. Specifically, for each resolver, we first find the domain intersection of it and each other resolver. Then for each domain in each intersection, we calculate the difference in their success rates on the two resolvers. Finally, for each type of resolver, we plot the CDF of the differences between this type to other types. The result is shown in the figure. A difference below 0 indicates a lower success rate of this type of resolver, and a positive value indicates a higher success rate. We can see significant differences for some types of resolvers. Domains resolved by 114 DNS and ISP are more likely to fail, while DNS pod, which belongs to Tencent, and 360 DNS, which belongs to Qihoo 360, have higher success rates. This observation partially explains the various success rates across public DNS resolvers. Then let's have a look at the impact of top-level domains. We inspect if certain top-level domains have lower query success rates. Specifically, we explore two camps of TLDs, the new generic top-level domains and those that have internationalized domain name. This table summarizes our results. We see rather different rates of success across the domain and query types. We next focus on new TLDs and explore the possible reasons for the lower success rate for new TLDs. The lower success rate for new TLDs may be because such TLDs attract certain types of domain registrant. For example, the .lol domain is well known to attract large volumes of malicious activities. With this in mind, we find a success rate of just 20% for .lol compared to 83% of .com. The presence of these unreliable malicious domains can be a reason for failed queries. To inspect this, we extract all A-record queries that were successfully resolved and investigate the network segments hosting them. This figure presents the distribution of the number of new GTLD domains and IDNs per network segment sorted by the number of IPs hosting new GTLD domains and IDNs respectively. We can see that the majority of domains map to a relatively small set of prefixes. Several surges in both lines further arouse our attention. They indicate the existence of some /24 network segments or subnets that serve a large number of new GTLD domains or IDNs. This is naturally driven by the presence of large web hosting providers. Thus, we extract the top 5 searches for both new GTLD domains and IDNs to explore their details. Due to space limitation, we only present the results of new GTLD domains in this table, where the last column presents the number of domains that are resolvable on 26 September 2019. Across all of these top ASs, we witness an extremely low rate of successful resolutions. In the most extreme case, we observed 201,000 queries for 195,000 domains being mapped to Anzu, none of which are resolvable today. In addition, the number of queries is close to the number of fully qualified domain names, or FQDNs for short, suggesting that these domains are short-lived and change frequently. The above trend leads us to hypothesize that some of these domains may be associated with malicious activities. To explore this, we leverage two blacklists from MyStotal and Qihoo 360 to check the domains. We label a domain as malicious if any of these two blacklists classify it as so. Due to the large volume of domains, we only check second-level domains. The results are listed in parentheses in this table. A significant fraction of the new GTLD domains fall into this category. After finding the prevalence of malicious new GTLD domains, we go one step further and explore the impact of these malicious domains. This figure presents the distribution of the number of end users' BGP prefixes requesting each malicious SLD. Except the SLDs hosted in Subnet 3, other malicious SLDs affect only one or two networks. In contrast, malicious SLDs hosted in subnet 3 have a footprint in dozens of networks, implying a larger impact. One possible explanation is that the subnets host different sites. Hence, this figure presents the makeup of the 5 subnets, confirming that they do map to different TLDs. Let's then move on to the implications of our findings on system design. We discussed about what systems we could build based on our observations. The first system is an active measurement system. Our results show that although IPv6 has been promoted in recent years, quality queries still fail frequently, and there exist resolvers that do not support quality queries. In order to understand which resolvers support quality queries, we can build a system to actively measure the IPv6 support of the resolvers. The system can distinguish between resolvers that support and do not support quality queries by sending DNS queries of popular domains that support quality queries. We can also test whether a domain supports quality queries by sending requests of this domain to resolvers that are classified as supporting quality queries. Considering the differences between resolvers, we could measure the success rates of domains by sending queries to different resolvers and use the result to help choose the better resolvers. In addition, we could compare different resolvers from the perspective of localization, where we could check whether the resolver directs users to remote servers. This additional function is motivated by our observation presented in this table. We calculate for each resolver the fraction of queries that redirect clients to servers in the same AS when possible. To calculate this ratio, we count for each domain its response IP addresses in the entire dataset. According to this result, we check for each log whether the requested domain is possible to be served locally and whether it is served locally. We observe that the obtained ratio differs significantly across the resolvers, which indicates that users can choose appropriate resolvers for better network performance. Therefore, it is useful to develop a system for end users to measure the localization performance of different resolvers. Such an active measurement system is useful for content publishers, ISPs, and end users. Many CDNs are being upgraded for better IPv6 support. However, if quality queries frequently fail, then the content publisher should be careful to use such CDN IPv6 service. Therefore, it is useful for publishers to locate their content if they can understand in advance which resolvers do not support quality queries. In addition, ISPs could also benefit when considering IPv6 network expansion, because understanding which domains support quality queries is useful for estimating the IPv6 traffic. For users, the measurement of different resolvers can help them to choose more suitable resolvers considering both IPv6 support and localization performance. We have found that malicious new TLD domains hosted by particular ASs contribute to higher failure rates. Manual inspection further reveals that the length of the second-level domains tends to be short. This table presents the fraction of malicious SLDs of different length. In more traditional or old or legacy top-level domains, malicious domains are usually long because registering a short domain name will cost too much for an attacker. However, registering short new TLD domains is much easier. Therefore, extracting features from domain names may not work well for detecting malicious new TLD domains. We could use features like DNS query frequency, the number of fully qualified domain names of an SLD, the resolved IP addresses, and the corresponding autonomous systems to build a system for detecting malicious new TLD domains. This slide summarizes our main contributions. Based on a unique dataset containing 3 billion DNS queries, we present a large-scale analysis of DNS query failures in the wild. We find that failed queries are indeed commonplace, with 13.5% of all queries not successfully resolved. This motivates us to inspect which factors correlate most closely with failed queries. We observe a highly skewed distribution, whereby a small number of domains are responsible for the majority of failures. In spite of the promotion of IPv6 over recent years, the majority of DNS queries are still for A records, and quality queries are particularly unreliable, with only 1/3 of queries successfully resolved, which suggests that IPv6 is far from ready. Upgrading the resolvers and popular domains for IPv6 is the first step towards the wider usage of IPv6. On the other hand, Internet users should be aware of the impact of using different resolvers from both the perspectives of query failures and mapping inaccuracy. We also find that the volatility of malicious multi-TLD domains contributes to higher failure rates because they change frequently and accesses to them result in failures. We finally propose two potential systems that could build on our findings. Thank you for listening.